Taking the engine as a point source of sound, the power radiates out in concentric spheres, so that the intensity at some distance r from the engine equals the power divided by the area of a sphere centered on that point, 4 pi r squared. If we write the intensity for two different spheres, the power is the same for each of them, so we see that the ratio of intensities on each sphere equals the inverse ratio of the square of the sphere's radii. So in part A, we can set I1 equal to 10 watts per meter squared, the intensity at a radius of 30 meters from the engine, and we can set I2 equal to 1 microwatt per square meter, the intensity of normal conversation. And we can solve the expression above for the distance R2, where that intensity is obtained. Substituting the known values and calculating gives us a distance of 95 kilometers. In part B, we're asked to calculate the sound intensity at twice that distance. The intensity goes as 1 over r squared, so if you double the distance, the intensity is decreased by a factor of 2 squared, by a factor of 4. So at twice 95 kilometers, at 190 kilometers from the engine, the intensity is 1/4 of its value at 95 kilometers, 0.25 microwatts per square meter. Part C asks for the power in the engine sound wave. That's the value of P from the expressions above, so we can calculate it at any of the given distances. We'll use the values I1 and R1, substituting them and calculating to find the power in the engine sound wave is 1.13 times 10 to the 5th watts.